All right. So today we're going to continue about main memory, and the lecture is a little bit in depth and requires again your attention because there are similarities between this lecture and what we're going to cover in the virtual memory, and maybe later on in storage as well. So just try to clarify if there's not, something is not clear. So last session we talked about memory allocation, how a fixed memory allocation or dynamic memory allocation works when OS wants to allocate some piece of memory to a user process. And we talked about how external and internal fragmentation can happen when you have either when you have fixed memory allocation, then you have internal fragmentation when you move processes around, and then you have holes that are available memory, but you can't fit other processes into them. That's external fragmentation. We talked about address binding, how you have multiple address spaces, and then between logical address space and physical address space. In order to do that, you have translation, and because of that, you have address binding. So you have symbolic addresses because later on your address, your real execution time, your addresses might not be known. So then at execution time or load time, the symbolic addresses or relocatable addresses again will turn into absolute addresses. We talked about how hardware plays a role in this, and how we can protect basically user processes from modifying or accessing the other user processes. Some of it was due to those base and limit registers, so the hardware can actually protect and make sure that the user process does not access wherever that is not supposed to. Obviously, OS plays a role in here because they have to set up the registers in the hardware. And we learned a little bit about paging and segmentation. So just a recap. So segmentation was for when you have different segments of code. Within each of them can have a different size. And then within each segment, the user process has a view of all of the segments, and it wants to access an offset within each segment separately. And now once you want to map that into your physical memory, then you assign each segment somewhere in memory, which does not have to be one after another. But then you take the offset, match the same offset. You just have a base register in order to for the OS or even the hardware to be able to map these base addresses. There is the segment table, which holds a table that maps the segments of the logical address space to the base addresses of the segments on physical memory as well as their limits. So then the MMU figures out where the actual address is and if it is valid or it's out of bound, right? So the same idea was also in the paging. Paging was fixed size, if you remember. So paging was for when you chunk the whole address space into, for example, 4K pages. And then you map each 4-page in the logical address space to a 4K frame on the physical address memory. The ones that are needed. Obviously, you have many processes. Each of them can think of 2 to the power of 32 bytes. But they're not going to use all of them, and you only have 2 gigabytes of RAM. So you only keep a page table, map the ones that are there. So we're going to see with an example how the bits work, for example. So again, just make sure that your groups are final. Again, if your group has not changed, you don't have to do anything. You should already have access to your project 2 repository. But if you are about to change, don't access it, don't modify any code, because that's going to just be removed altogether, right? All right. So today we're going to talk about the implementation of paging and multiple level paging. We're going to talk about effective access time and how caching is going to help. And we're going to talk a little bit about the Intel architecture, how it implements segmentation and paging. All right. So this was the example that we didn't cover last session, so I'm just going to go over it again. So if you remember the dynamic allocation, we had holes and we had processes to fit on the memory. So for those, we had 3 algorithms, just first fit, which was to pick the first hole that is big enough for our process. Best fit is choosing the hole that is big enough, but also not too big, like the smallest one that can fit. Worst fit is the opposite of that, so the biggest, basically, that is available. So this was the example, and I'm going to just go over it on the blackboard just to see how it works. Okay. So it says that given 5 memory partitions of 100K, 500K, 200 and 300, and 600K. It says they're in order. How would each of the first fit, best fit, and worst fit algorithms place processes of 212K? So these are whole. I'm going to write a little bit larger on that side after that. And these are processes. 212K is the first process. 417K, 112K, and 426. All right? Yep, that's it. Which algorithm makes the most efficient use of memory? So when we have these holes available on memory, that means our memory, if you look at it like this way, increasing the addresses on memory, sometimes, for example, in the user program discussion, we have it like flipped because that's the way that the diagram is there. But a lot of the cases, we just like have it increasing addresses on this side. Just note that. So the first hole that we have is 100K. So, we have some unavailable memory or allocated, and then there is 100K hole here. And then the next available is like 500. Again, we may not have something here. And then we have like a 500K available here. And a 200, okay. Let me just like write down the availables and then make some space with that. So, just like this much, and then 100. And then, like, a 500. Then 236, right? So, just remember that these are not proportional. These allocated or used memories can be much larger, obviously. Alright, so these are the holes available, and now we have like these processes. The processes come one at a time. So the first process comes, let's do first fit. So 212K comes. The first fit is the first hole that fits it. This one, right? That's easy. So then this will change. So this will now be occupied for 212K and available 288K, right? This hole now still going to be there. So next, when the 417K comes, we again start like, checking. So does it fit? Doesn't fit? Doesn't fit? Doesn't fit? It fits here. So again, this will be the allocated memory to that process. And now we have 183K available in the end, right? So the next process comes, 112K. First fit. Doesn't fit into this, it fits into this. So now it will change again. We will allocate some memory here. And then we have 112. That's 176K left. Okay? You can basically also redraw the whole table every time, if that makes it clear, but I just wanted to make it simple. So 426K. So it doesn't fit here, it doesn't fit in here, does it fit in here, not here, not here. So we cannot fit the 426 process, right? So this we cannot fit. Okay? That's first fit. So we're going to go for best fit. Any question in this one before I wipe it? Yep. No. That has to, I guess, like wait. So the operating system cannot like, if it can wait, it will wait. It depends on the implementation. If you don't have So this is like a simple concept. So a lot of times you have swapping, so you make space and saves data from memory to disk. But in this case, at the time that it requests, at this time we cannot fit into memory as is. All right. So best fit. So for best fit, you remember that we should choose one that fits, but also is the smallest. So when 212 comes, it doesn't fit into this. It fits into this. It fits into this. It fits into this and this. Which one is the smaller? The 200K, right? So we're going to allocate 100. Oh, it doesn't fit into this. I thought it's this one. So yeah, it doesn't fit into this. So we're going to pick the 300. We'll fit the 212 into this, and now we have an 88K. And you already can see the best fit. The issue with best fit is external fragmentation, because you will have small chunks of available memory which are not that useful for the other processes. So 417 comes. It fits into this. It fits into this. So this is smaller. So we're going to pick 417. We're going to allocate the memory here, and we're going to be left over with 83K. Right? Next, 112 comes. It doesn't fit in here, it doesn't fit in here, it fits in here, it doesn't fit in here, and it fits in here. So 112K will assign this, because this is smaller. So allocate 112. You can also write down, by the way, the number if you like, that helps. I don't know which one is this one. This one is 417, right? So this one is 112. And then you have 88K again available. And then the final process, when it comes 426, doesn't fit here, doesn't, and it does fit in here. So again, you allocate 426 in here, and then you have 174 available. So in this case, actually, we could fit every one of these processes, and we have those fragmentations available. All right? Any question in best fit? Yes.
Not in best fit, but I have a question there. These three different types of fits. This is not dynamic memory allocation.
Why not?
Because dynamic would have to change as you go.
No, dynamic is very in contrast to fixed, and fixed is the amount of memory that we're allocating is not fixed because it's equal to the amount that the user process is asking. So the fixed would be that for each of them, no matter how much they want to use, we should have a chunk of memory, for example, as 1 megabyte, and then assign that. And the problem with that would be not the external, because they would all align together, but it would be internal fragmentation, because if you assign 1 megabyte to, for example, this process, no other process can use the rest of the 888K. So this will be unused memory within those allocated space. But yeah, dynamic is different. This is just like a very simple concept of allocating, just loading a process. The fact that it's there, you can have on-demand pages or dynamic loading of processes. Even I made an example that a process, when it loads, it does not have to load completely. It can just load some part of it, and as it goes, it wants to load or call some routines, then it can load more code. That's just a little bit different. Yeah. Okay. All right. So the worst fit, I'm going to do a little bit, if I can, faster without mistakes. So 212, we're just going to pick the biggest hole. So it's going to be this one. So we're going to just have 212, and then you have 388K here. And then when the 417 comes, it doesn't fit in this one, so you're going to pick this one, 417. And then, as you can see, the external fragmentation of worst fit is not that bad, because it leaves useful memory spaces from the big holes. I mean, that's just again, different ideas and approaches. So this one leaves 83K. Here, 112K doesn't fit into these, but we have two holes here, so we're going to pick this one. 112. We'll be left with 188.
At the bottom, 388.
Oh yeah, actually we do that. Thank you. I wanted to rush it. That happens. Good catch. That was actually one of the points of this example. 112, you have like 276K available here. And 426, again, you cannot fit because for this example, you won't have a big enough hole. All right? So in this example, best fit, use the memory more efficiently because we could fit all the users and processes. All right?
So
Yes?
for workspace, it'll always choose the biggest spaces to allocate processes?
Yes.
Okay.
Allocate the largest hole, must also search entire list. Okay, actually I will do it.
Then how do you reduce internal fragmentation?
What's that?
So then how do you reduce internal fragmentation?
In this case, we don't have any internal fragmentation actually. No, they are still fragmented because the amount of memory we allocate to each user program is the amount that they're going to use. So we're not wasting memory in the sense that these holes are available. We can allocate them. The problem is we cannot. It's not. It's not enough. It's not big enough for processes. So that's why it's called external fragmentation. Internal fragmentation, it's within the allocated memory, but it's not used by that process, so no other process can access it. So it's not available to other processes. And one of the ways that last session we talked about to get around this problem, external fragmentation, is to basically defragment, just like stack them up or something, move them around, if you can move the processes at execution time. Okay? Okay. All right. So now the address translation scheme also we talked about last session how paging is actually working. So when you have a memory address, for example, 32 bits, right? Each memory address is like 32 bits of like zeros and ones, right? Highest bit here, and then the lowest bits over there, right? So the way that you work is that when you want to map addresses from your logical space to the physical space, you cannot map every address to every address. One of the reasons would be what? Someone tell me. If you want to map every used logical address to a frame of your physical memory, so that any address that you want to access here, you look it up and then you access it there. What's the problem of doing this? How do you want to map it again? Do you remember? How do you want to map from this address space to this address space? How does the computer do it? Huh? It's on the... Yes, it's a table. It's a page table. You remember. There should be a table so that I look it up. Okay, where does this address, point to, or I should map it. So if I have 2 to the power of 32 or 4 billion addresses in the logical address, right? If I want to map every one of them to one physical address space, how big should my table be? 4 billion entries. Each entry should also tell me which address maps to a full address. So the table itself will be much bigger than the memory that you have or need. So that's why the pages have a size and the offset is working. The reason is because you want to have a table that is useful. So you split your address bits like this. If you have n bits, 32, you define an n, 12 bits, for example, to a page offset. What this does is that it reduces the number of entries that you need in your page table. So if you have 32 bits here, and you have 12 bits in here, then that means that your page number can only be from 0 to 2 to the power of 10. That's only 1,000 entries. An array of 1,000 is not that big. And also, each entry needs to point somewhere in physical memory, right? But because each page and frame should also be of the same size, right? When you are mapping this number, you map it to the same size number, right? So you don't map like a 10-bit number to a 15-bit number. That doesn't make sense, right? I mean, sometimes it does, but in this case, it doesn't, because both of the address spaces are 32-bit, okay? So when you have like 10-bit for each entry, your table, the other dimension of your table is also shorter. So it actually, you can fit it. So, for example, let's say if this is 10-bit, then each entry can take only 2 bytes. 1,000 entries, that's like 2,000 bytes, 2 kilobytes. Page table of 2 kilobytes is not that big, right? So you can do it. Now, again, the problem would be by moving this here and here, you have like a trade-off. As you do this, the pages get bigger, and because they're fixed, then the internal fragmentation happens. But the page table gets smaller, which is good, easier to handle. As you move this here, your pages get smaller, your internal fragmentation gets less, but your page table gets more and more. Okay? So, let's see. If again, this was the example over there. So wherever this is the page index goes into your page table, and the frame, the part of the physical address, which is again the portion of the frame, is read from here, and then the offset is added. This works with binary numbers. If you're comfortable with binary numbers, it's simple. Whatever numbers you cut off, that's just dividing a number, or taking chunks. When you have this number and put it on the MSB, add 12 zeros in front of it to get the first byte. That's just taking bigger steps in the chunks, or it's like multiplying that by a factor. Okay. So, but how do we implement paging? Because this page table, where is this page table? Where is it? It has to be somewhere where it's accessible. It's also not very, it also is, depends on the process. So the page table for one process is not going to be used for a page table for the other process, because this process is using these pages which are mapped to these frames. This process is using these pages which are mapped to these frames. The table does not, so where it should be? So it should be kept in memory, because first of all, where else? You don't have a space on your CPU to hold all this data, and you don't want to store it on the disk, because every time you want to access the page table, if you want to access your disk, that will be too slow. So it should be somewhere in memory. And it's going to be in the PCB, process control block. Again, because it's part of each process, so each process will have their own page table. So then we have a page table base register. So this is in hardware. When an OS wants to load a process or context switch, it will read the page table from the PCB, the process control block, and then loads these base registers and length registers to the CPU. So the MMU can access this on memory, because this should happen in hardware, right? Whatever the CPU wants to access, this has to happen. The address should be broken down, access the page table on memory, and then read the offset, whatever. So this is happening in hardware. So in order to do that, the hardware should know where the page table starts and what is the length of the page table, so that, if the page table has 100 entry and we want the page 200, again, the hardware should be able to trap it. So this is why they have to be loaded by the OS to the registers, so it can happen in the hardware. So, but the problem is this, again, is even if it's happening in the hardware, every instruction of the CPU that wants to try to access a memory location, it is now using 2 accesses. Why? Why is the access time doubled now? Yes. First, we have to look it up, right? The user process instruction says that, okay, I want address 1000. So every time, the MMU should first access memory because the page table is in memory. Load it. What is the page that the address 1000 falls into? Okay, this is the the frame number. Now I will add the offset to it, and now I access the memory again to read this byte. 1 access to the page table, 1 access to get the data. Next instruction. Now save this, the result of my calculation into address 2000. Okay, it might be on a different page, right? So where is 2000 falls into? Okay, this frame. Now I'll add it, store it, right? So each access to memory will be now twice. And then the 2 memory access problems can be solved by use of special lookup table, which is called TLB, translation look aside buffer. So this is one of the one part of the evolutions in CPU. So because your CPU is small, it can work on higher frequencies, right? Gigahertz, for example. And also the type of the memory inside them is static registers, which are much faster. Your RAM, on the other hand, uses a different type of technology, so it can be so huge, like 4 gigabytes or something, right? And also the bus is now, it cannot support like a very high frequency like gigahertz, right? Internal clock can, but again, the bus, it cannot. So the access time to the RAM is very slow for the CPU. It's very fast compared to the disk, but it's very slow for the CPU. So they have like caches and, some other registers so that they can handle and speed things up, because you don't want to divide the speed of every instruction just by 2 like that. That's just not tolerable. So this is a buffer within the CPU to help this speed up. Okay? How we do that? So the TLBs are very small. Again, remember, whatever that is in CPU, they're small. You have only few kilobytes of level 1 cache or TLBs. Okay? And it holds the pages, the recent pages. So instead of accessing the page table every time for every address, if you want to access the same page, you don't need to do that, right? So as long as you have memory, you have it in the CPU that, okay, this page is this frame. Okay, next address comes. If this is within the same page, I don't have to access the memory anymore. I already have what the frame is, so I only access the physical memory once. That saved us just it's sped up twice. So if I have 64 entries in the TLB, the most recent 64 pages that I have access for this user, and I know the mapping. So any address that comes within those pages, I don't have to look at the page table anymore, right? But what if it is a new page? I have 64 pages from let's say pages from 0 to 63, and now the user space wants to access page 50. So now it's a TLB miss because I look it up in the TLB and it's not there. So what I'm going to do is that I'm going to look at the page table, read the page number 50, what is the frame, also bring it into the TLB, replace an old or whatever, depending on the algorithm. You replace one of the entries, and now you have that page. And it's actually pretty useful because the way that the programs work, they don't access random places by themselves, right? If your instructions are, in one segment, they're one after another, right? Instructions run after another. And they have a loop, or, if you're accessing one data, chances are that you're going to also access the next piece, right? Unless you jump to a subroutine or, some of these big jumpers, the distribution of memory accesses are pretty, close. So once you have something like that in the cache, it's going to save you a lot of time, right? But also, something that we can do is the TLB, as we are replacing pages, we are basically now losing the old entry there, right? So if we had like from 0 to 63, and now we access the page number 50, we have to replace one of them. Which one? Okay, let's say page 10. Now when we replace it, page 10 is not going to be there. So if in future page 10 wants to be accessed, we have to bring it up again. So instead, you can have some of the entries to be wired down. Tell the CPU, okay, these entries from 0 to 10, don't change them. Okay, that was loud. Don't change them at all. Keep them, replace other pages. What would be this useful for? Most frequent, or some other notion would be also important. For example, kernel codes, right? Whatever is happening in, if because the pages, the OS already knows what are the pages and where it's at, so it knows which page entries will be accesses to the kernel code, so it can always keep those pages in the TLBs for faster access, right? So the kernel piece code at least would run faster. So this is again something else which is unique to processes. So the cache which is in the CPU holds some page references and mapping, right? And you remember, each process has a separate page table. So if I held page 0 to 63 for this process and I have them mapped to the physical memory. Now what happens if another process comes and they also use page 40? But their page 40 is definitely not mapped to the same frame there, right? It's somewhere else. But now if they access page 40, CPU might say, okay, do I have page 40? Yes, I have it in my TLB. So it will access the other user process, right? So the problem is when you context switch, the table should just be flushed. Because the table is a cache for the page, the TLB is a cache for the page table for that process. When you context switch to another process, that is just invalid. So instead, one other way is that you keep the translation look-aside buffer TLB, you keep it, but you keep also an identifier of the process. So if the next process wanted to access the page 40, it is also a different process. It has a different ID. So the CPU checks, okay, do I have the page number 40 for that process? It's different now, right? But the good use is that you don't have to flush your TLB every time, because if you're switching between two processes, every time you access the whole page table, not just once, for every entry, you have to access the page table to be able to bring them to your TLB. And then you use it, you switch to the other process, again, flush it. Access, again, multiple entries. So if you can keep those, that will just speed things up again. Alright? Any questions on TLB? It might not be as, obviously very clear, but, within a couple of examples it might help. So let's see. So this TLB is in the CPU chip itself. So when a logical address is generated by the CPU, first it looks at the TLB. And one good thing about TLB is, again, because it's implemented in the hardware, it does not, the address is compared simultaneously. So it's a lookup table. So even though you have the entries are not sorted. So whatever that usually how arrays work is that you have entries from 0 to 100, and when you want to check what is entry 60, you add the 60, look at this, and then read it. That's how you actually use sequential arrays. The TLB is different because TLB has 64 entries, but the entries within the entry indexes can be some random numbers. The first entry might be page number 1000. The second entry is page number 2000. Then page number 4. So there is there's no way that you can predict which page is in which index. So normally, if you want to write it in software, you have to look at all the entries one by one. Are you 1000? Are you 1000? Are you 1000? Are you 1000? If you find the 1000, then you break the loop and then read the frame. That's how you should do it in software, right? But in hardware, it's actually much faster because in real time, it compares thousands to all those registers and then one of them will only respond if the 1000 is in there. So it's just like immediately. So a logical address is reference. The page number goes into the TLB. If it's a hit, then it will just generate the frame instantaneously, which can be added to the offset and then immediately accessed, right? So one memory access. If it is a miss, if it's not generated or invalid, then we have to access the page number to the page table, and we have the page table already in memory, and we have the base register and the limit registers in CPU, so it's accessible, but it's just like, takes longer. So we access the page number in the page table, read the frame from memory this time, bring it into the TLB, and also access or dereference the memory address. Okay? So now the effective access time is something that is calculated, and this is very important not to confuse it with effective access time for when we have like virtual memory. Okay? It's the same name, the same concept, but just for different uses. So this is an effective memory access time, like an average, right? So if we don't have cache at all, every memory access takes exactly 2 memory access in this scheme, simple scheme, right? Now, if we have cache, it's gonna like some of the entries are gonna be in the cache and faster, some of them are not gonna be there, so that they have to still be 2 memory accesses. So what is the average? So this is defined by this hit ratio, alpha. So if we have a hit, the amount of time is 1 memory access and 1 cache access, right? So we have a cache access in the TLB, and then once we have the frame, we access the memory, that's it. On the rest of the cases, 1 minus alpha, we have 1 cache access to see if we have it in TLB. If we don't have it, we have 1 memory access in the page table, and then we get the frame, 1 memory access to the physical memory to get the data. So the effective access time is this. But usually, cache table access is just like ignore. You can just ignore it, because it's like not comparable to the memory access, like orders of magnitude, right? So just you remove them, and the effective access time is like, in the alpha ratio of the time, whenever you have a hit, you just like have 1 memory access. If you don't have it, it's a miss, you have 2 memory access. Simpler case, you have 1 memory access anyways to get the data, but in alpha cases of the time, you have it in the memory, in the TLB, so you don't have to read the page table. In 1 minus alpha, or the misses, you have to access memory 1 more time to get the page table. Right? So this is effective access time. As an example, if we have a cache that whatever, depending on the size of the cache, algorithm, whatever, on overall we have 80% hit rate. That means on 80% of the time, whatever that pages that we want to access, they're already in TLB. 20% of the time, they're not. And let's say a memory access time is 100 nanoseconds, right? So the effective time would be on 80% of the time, we have only 1 memory access. On 20% of the time, we have 2 memory access. So 120 nanoseconds, right? And if you increase this alpha or the size of the TLB, however, that the hit rates will go up to 99%, for example, then the effective access time would come down to 101 nanoseconds, which is much closer to this, right? So that's also similar to how caches work in instruction cache or data cache. And the hit rates are actually 99.9 or 99.99, whatever, right? They're pretty close. That's how, they have evolved. All right? Any question?
Yeah.
Yep. This is 1 memory access time. This is 2 memory access time.
Okay.
Yep. All right. So a page table now. Let's see. How is it practical? So it can get huge, right? The number of entries and the size. Again, there's always a trade-off. But even with that case, let's say, for example, a 32-bit address space, you have pages of 4 kilobytes. Again, if you have like 2 big pages, internal fragmentation would be too much, right? So then your you will have 2 to the power of 20 entries in your page table, which is like 1 million, right? So 1 million entries. Now, if each entry is also 4 bytes to basically hold the frame bits, that would just like need 4 megabytes of physical address space memory for page table only. So for your process that might use whatever, like, even smaller memory, you only need 4 megabytes in your kernel PCB just to hold the page table, which doesn't make sense. It's just like too huge, right? So, you have to also have this 4 megabytes contiguously, right? Because your page table, when you want to address your page table in memory, you just like move in the index. You have a base register, right? And then you want to now access the entry of 1 millionth. So this has to be contiguous. So that's going to be very expensive, practically. It might have been good for 16 bits, but not for 32 bits. So one way to do it is actually make it hierarchical and, for example, split it into 2. So the paging itself is also paged, right? So you break it up, and your page table, instead of like being one huge page table, you break it up and page itself. So you have an outer page table that will tell you chunks of your page table will be mapped, instead of like contiguously, at different parts of memory. And then you have an outer page table that says, okay, page entries from, for example, 1 to 100 are in this location in memory. Page entries from 200 to 299 is going to be pointed, for example, in this part of memory. Page entries from 300 to 399 are pointed like this, right? So this way, if you want to access a page, you first look, okay, what is the page? It's like 476. Okay? So 476 resides in this. What is, first of all, where are the pages from 400 to 499? For example, they are here. Now, what is the 470th one? It's in here. Where is it mapped? Here. Now you have also the offset of the frame you added and accessing. So you have to break it up because your page table is now, too huge. But the problem is now you have like more access time because you have to access first this, and then that, and then that. Alright? So, when you have like 2 level, like in this case, a page number, for example, consists of 20 bits, and a page offset consists of 12 bits. Again, 4 kilobytes of page or frames. Now, you break it up to 10 bits, okay, for the page table itself. Let's see. Your logical address is now here. A page number P1, a page number P2, like this is outer, this is inner, and then the page offset itself is always there, right? We don't have that. So, it's called like forward mapped page table. So what happens is that first you access this page P1, like Intel calls it page directory. You first look at, okay, where are these, range of pages in memory. Then you find it, then you look at this entry within that directory. And then you actually read the page or the frame which is mapped on memory, and then you add the offset, you move it. Alright? So this picture actually tells it all. This is like, the page directory, and then these are the small page tables. And then first you access the entry within the directory, and then you find the page table that you're looking for. You look at the inner page entry in that, and then you find the frame. All right. So this is the translation again happening. So the same thing. So this one is the entry within the outer page table or directory. Within that entry, that points us to another page table which is smaller, but somewhere in memory that is not necessarily contiguous to the other ones. And then P2 is accessed to get the index of that frame, and now we have the frame. So at this time we have the offset from the frame and page. At hardware, these will add up to get the exact memory address. Okay. So this is now gonna like have an example of our Intel architecture. Before this, you have to like these are not as important. This is just an example, right? So you don't have to memorize whatever the Intel does, but because it's like widespread, it helps to understand how it does it because it's basically practical, right? So before this, if you have any questions, just it's now's the time. We can go back to the slides. We can go back to the example, whatever. No? All clear? Yep. So if now there's a question of this, will we all be able to answer it? Okay. If not, that's okay. Again, memory and translation, it's a little bit not straightforward. And unless you actually kind of like see an example and do it, it's probably not going to be clear. But please read these slides from the Tuesday and today during the weekend or whatever, because when we want to move on to virtual memory, you have to be clear on these. So if there's anything, we're going to clear it up on Piazza. Piazza is not just for your project, but also here, hey, I didn't understand, this is slide number, whatever. We're going to be able to clear that up, right? So for Intel, it supports both segmentation and paging. And the reason is because in older CPUs, they had segmentation because it was one process at a time, and they had access to basically all of the memory. But they wanted to use segments because they had like code, they had like data, they had like stack, whatever. So the segments was there, and the programmers could use it. And now when we want to use, when we have now an operating system, the operating system wants to allocate memory to processes. Each process still behaves the same, right? It's an abstraction. The processes don't know that they're running on an operating system on a different CPU. They think that, we are still hanging out on the CPU by ourselves. So for that purpose, it should be backward compatible. So they support segmentation, but also paging for that matter, right? So now IA82, IA32, which are the family of Pentiums, for example, they can cover, or they can support the segments of up to 4 gigabytes. So you can have one segment that is like the whole space. But also you can have up to 16K number of segments for each process. So they can be very small size segments, but the way that it allows is that. Now, it is the segment themselves are separated into two. One is the 16 number of segments, 16,000 number of segments is divided into a local descriptor table, which are segments specific to this process, and one is global descriptor table, which can be shared among all processes. If you remember, last session we made we went over an example that when the operating system is there, some pieces of code in the operating system does not make sense to have multiple copies for each process, right? Because each process just wants to execute this piece of code, and this piece of code is the same piece of code, no matter what you want to do, right? Let's say this is like a routine of calculating 2 to the power of something. The code is there, right? So it's just like that. You should put it in a segment, and that segment be accessible to all processes. So if they want, they can just run it. So we have this 16K entries will now be half and half. So now this we have the logical address have a selector part, which is 16 bits. The first 16 bits of the address is the selector. Now the selector has 13 bits of segment, which is 2 to the power of 10 is 1,000, and then 2 to the power of 3 is 8, so that's 8,000 entries. And then you have like 1 bit for like a partition. So which partition it is? Is it like the global one or is it the local one? So altogether, these 14 bits define the 16,000 segments. Which segment you're referring to? And there's also like 2 bits for, I think, like protection. So this will basically goes into the segmentation unit, and then that will tell you a linear address. A linear address is still logical. So even within one process, right, you have the 2 to the power of 32-bit address space. Now you have, again, you remember, the one process wants to use a stack, code, data. So the user process does not want to, address each entry absolutely. So it says that, okay, I have a data segment, it's somewhere in memory. Now I want an entry, the third entry in that data segment. So the fact that the user space is saying I want data segment shows the base. It's in here. Now I want the third entry in that data segment, it defines this. But all in all, we are still talking about the logical address space of this user process. Right? So this is called the linear address. So this is still logical. Now, this goes into the paging unit, as we just learned today, and actually get the mapping into the physical memory. Right? And also, paging, again, can be either 4 kilobytes or 4 megabytes. And the reason is, I'm going to see in a second. So the segmentation and paging units of they're together, they're the MMU that we've been talking about, right? How they map the reference of the CPU to the physical memory. Okay? So here it is. The CPU generates one logical address. It first goes to the segmentation unit. Depending on which segment it wants to access and which address within that segment, it turns into a linear address. That linear address is still in the user address space. So it goes into the paging unit and then gets the actual physical address, and then you access the memory to retrieve something. So the 32-bit is basically divided into this: page offset and page number, 12 bits, 10, and 10. So if you remember just now, we went over two-level paging. The problem with two-level paging was that it had two level of access time to page, right? So that's why they had the option. Either you have 4K pages, 12 bits, then you have 20-bit page numbers, which you have to divide into 10 and 10. So you have a page directory and a page table of this size. Or they also provided the option that, okay, you can have 4 megabyte pages, which is all the way from here to there. Then you don't have 2 access time anymore. You access only 1 page table and directly get your frame number. So that's why it's either this or that. In concept, you can, basically have any of the between, but it just doesn't make sense. They implemented 2 of the options, and in hardware it's implemented simpler, right? So the logical address selected by CPU is first each user space does not have any paging or anything. That's happening later. From the perspective of a process, you have segments and offset within segments, right? So the 32-bit has the selector and offset, 16-bit each. The selector goes into the segment table here, the segmentation unit, sorry. There is a segment descriptor that tell what is the linear address. You add the offsets, you get the 32-bit linear address. This is still within the user address space. Okay. Then this linear address, again, is just 32-bit, is either 4K pages and 2-level paging, which then goes into the paging unit. Again, with the TLB, we still can handle this in the hardware fast. The page directory is first accessed. Within that page directory, the second level or inner page tables are accessed. We check the inner page index into that page table. We get the page. We add the offset, and then basically access it from memory. Now, if it's a 4 megabyte pages, we have 22 bits for offset, and we have only 1 page directory. Within the page directory, we don't have a pointer to a page table. We have the actual entry of the frame itself. With 1 access, we just read that. We add the offset. We get the memory. Okay? All right. So we have a few minutes, so please hold on as we can clear things up. So first of all, again, just follow whatever is going on on the Piazza for groups. If your group has not changed, you can start working actually. Start, compile, and run one of the OS tests from user prog. One of the things is that at this point, obviously, it's going to fail, but at least you have to be able to see that it's like compiling and failing, and how to run the test. If you remember, or if not, go back to the recitation slides or project 2 discussion session. Project 2, you have to create a virtual file disk. You have to ask Pintos to format it. You have to compile examples or test files and then copy them into that virtual file disk. So instead of like doing just make check or make grade, try to, do a make check and see what commands it's generating one at a time, and then just pick one of those commands and break it up. It uses Pintos -v, -k, -f, -q, whatever. Break that up and only try to run that, for yourself. So, read these slides and start it with however that we talked. So you have to change the stack pointer. You have to change the process weight. Once you start that, try hex dump. Use hex dump just to see where the stack pointer is pointing, what are the data there. Because that's where you're going to start your project too, with argument passing. Okay? So please do it by the next session. If you have questions, stay. If not, please.